All right. So our next plenary session, you'll hear from a couple of our early career and science highlights. And our first speaker is going to be Victoria Forsyth. Oh, here we go. There we go. He'll be talking about Anchor, a new approach to ionospheric data assimilation. Yeah, so the way this works, so that's forward, backward, and you kind of like hold it down for a second, and then you can move it around like that.
That's pretty cool.
Yeah, it's actually kind of neat. No, like a hand mic? No. Sorry.
Yep. Hi, everyone. Thank you so much for giving me this opportunity to present this talk about a brand new data assimilation model that was developed at the US Naval Research Laboratory. And before I start, I would like to thank and acknowledge my teammates that are listed there, list is long. So the ionosphere. Well, the global structure of the ionosphere is controlled by solar illumination and plasma transport. It is tightly coupled with neutral atmosphere and with the magnetosphere, because this is why we have in the next CEDAR joint with GEM. It's important to nowcast the electron density in the ionosphere. And the way to do it is by fusing the model prediction with the observations. And this fusion is called data assimilation. Why do we need ionospheric data assimilation at all? Well, there are two reasons. First reason is kind of like operational perspectives. Especially from the Navy point of view, we do need to know the current condition of the ionosphere, because ionosphere can interrupt or cause the signal loss. It causes radio signal delays. It bends the ray path. Plus, high-frequency communications heavily rely on the ionosphere. To establish those communication links between, let's say, one ship and the next one, we need to know the ionospheric conditions to choose the right frequency of the signal. Plus, over-the-horizon radars, they also heavily rely on the conditions of the ionosphere. That was operational reason. Scientific perspectives. We can use ionospheric data assimilation to study large-scale ionospheric structures. For example, storm enhanced density, ton of ionization, ionospheric trough, equatorial anomalies and plumes. Also, we can study smaller scale events, such as polar holes or polar patches, but to realize this connection of those smaller scale events with the kind of to give it a larger picture. For example, we conducted one study where polar holes were first detected using incoherent scatter radar data, but then we used ionospheric data assimilation to see from what place the plasma were coming to before getting depleted. Plus, we can use ionospheric data assimilation to study large-scale ionospheric waves, subjects like coupling between southern stratospheric warming and ionospheric perturbations, third-ional migrating tides, tidal waves, and I'm sure this list is totally not complete, and this list of references also. I'm sure there are a lot of studies that use the ionospheric data assimilation to enable science. Coming back to Navy, we had certain goals for a new data assimilation system for the ionosphere. Since we need ionospheric data assimilation to nowcast the bottom side of the ionospheric density, we needed to do a better job to specify bottom side ionospheric parameters. Sometimes ionospheric data assimilation focus on the vertical total electron content. And usually, if it's a three-dimensional ionospheric data assimilation, what I mean by that is that if you look at the electron density profile, this profile is kind of a distribution of the vertical grid points. So if data assimilation is done in this three-dimensional sense, sometimes the results for the vertical total electron content looks wonderful, but if you look inside of each profile, kind of to check if your HMF2, NMF2, the total structure of the vertical profile, sometimes those results cannot be reliable. And it's like you do a good job in terms of vertical total electron content, but at the price of keeping the structure of the electron density profile. We also needed it to be very fast because we want rapid reanalysis once the new data becomes available. And this is how the anchor was born. So anchor is a parameterized data assimilation model. So to construct the electron density profile, you only need 12 parameters. You need 3 parameters for the peaks of F2, F1, and E regions. You need 3 parameters to describe the heights of those regions, plus you need 2 parameters for F2 region, for the top side and the bottom side, 1 parameter for the thickness of the bottom side of F1 region, and 2 parameters for the E region to describe the thicknesses. However, we choose just 5 parameters to do our data assimilation. We choose NMF2, HMF2, thicknesses of F2 region, and NME. But we update all of the other parameters the way they are related to those main parameters, kind of like IRI model does it. IRI model simulates the main parameters, such as the peak density and its height, but then it calculates all of the other parameters as dependent parameters from the main. There are several components to data assimilation. First, it's a background. Then we need to find the background error covariance matrix. We need to establish our observations. We need to construct the observation error covariance, and then we need to have some sort of engine for data assimilation. So first I'll talk about the background, the first component. Specifically for this project, we developed a tool fully in Python, future generation of students, fully Python tool, that calls PyIRI. It's not just a simple rewrite of the old Fortran IRI code. That was a remake of the IRI. Okay, let me first explain how classical IRI works. Classical IRI takes one position on the globe and generates the electron density profile. Then if you need to run IRI for another position, this process happens again. So to construct the global map of the electron density, like three-dimensional, you need to run IRI over and over and over. For our purposes, we also have not a classical geographical grid. We use MLT quasi-dipole latitude grid. So for each time frame, we have a new position of the longitude and latitudes for our grid. So for every 15 minutes, we would need to calculate the background for the new set of coordinates. So to run our data simulation for 1 day, we would need to run Fortran IRI code 6 million times. And of course, that's a lot of time. So we developed this tool to fasten up this process. And it takes only 3 seconds now to obtain electron density for the entire day, for the entire globe. Please use it. So if you want to learn more about it, there's a paper in Space Weather. Plus, we made this tool fully open for the community. You can download it from GitHub, or you can use PyPy to download it. So it's just one command, pip install PyIRI, and it's all yours. Next component of data simulation, background error covariance model. That's a very important component of data simulation in general. It defines how the data propagates from the location of observation to all of the other locations around this point. How fast this drop from data to model occurs. So we construct background error covariance for each day of our data simulation. We collect all of the diurnal frames of pi ri, find the mean of them, find the deviation from that mean, and then for each location, we find correlation with all of the other points. And this plot shows how those correlations look like. So all of the black dots are the reference points, and they show how the correlations drop from one reference point to all of the other ones. And it's not just boring simple ellipses. Look at the 12 MLT. We have those secondary peaks, and what it tells us is that if we ingest our data point at that location, not only the model data at the particular location will increase or decrease, but also on the opposite side of the magnetic field line, this information will propagate there. Next section, observations. Currently, Anchor can ingest ionization data, radio occultation data, and slant total electron content from ground-based GPS stations. I'll start with the easiest one, radio occultation data. So because we're working with parameterized model, we decided that we need to massage our data as much as possible to extract all of the ionospheric parameters, and then we ingest not the entire set of observations, but only those parameters into our model. So radio occultation happens when a low Earth orbit satellite communicates with the GNSS satellites. Sometimes the geometry happens that LEO satellite is kind of lower on the opposite side of the Earth from the GPS satellites, and that's when the slant total electron content can be measured, and it kind of scans the ionosphere. The raw measurements are slant total electron content. Oops. Then we apply Abel inversion technique to convert those measurements into electron density profile. It will not be a vertical electron density profile. It will be electron density profile around the tangent points for this radio occultation. So the profile, back. So the profile looks like this. And then we apply least square fitting to find the NMF2, HMF2, thicknesses of top and bottom side, and the peak of E region. And that's how 1 hour of observations of cosmic data looks in our MLT quasi-dipole latitude grid. So then we record the locations for our observed NMF2, HMF2, and they're shown with dots here. And we'll also record all the thicknesses, and we ingest them all as point measurements on the map of particular parameter. So now this data simulation engine. Oh my gosh. Okay. So we start with background. This is the map of NMF2 in our MLT quasi-dipole latitude coordinates. In general, to establish data simulation system, we don't start working with data right away. We first make so-called OSI, Observed Simulated System Experiment study. So what we do, we say, okay, let's take another model and let's call it a truth, like a known truth. In this case, we used SEMI-3. Then we simulate all of our observations based on this known truth, and then we treat them as data. This is why we can see how well our data simulation system works, because we actually know the known truth. So we simulate our measurements based on truth, and we ingest them. So this is how the analysis looks like. We produce analysis, again, by simulating background with our observations using this equation, which is Kalman filter equation. And that's how our percent difference looks like between the background and the analysis. So the color around the points show how the background model was corrected by the observations. And we do this step for all of our 5 parameters. And you see that NMF2 changes are very insignificant. It means that pi-array model does really good for NMF2. For NME, yeah, slightly higher difference. And that actually demonstrates just the difference between, of course, SEMI3 model and the pi-array. But usually, and that's the case that we see with actual data, the thicknesses of F2 regions are always really, really corrected by the data. Like the difference between observed thicknesses and the model is really high, meaning that modelers, we need to do better in terms of figuring out the thicknesses of the F2 top and bottom sides. All right. So now we check how data assimilation improved our model. So we calculate root mean square errors, and I show all the root mean. Sorry, I'm lost in this clicker. I'm showing root mean square errors for all of those parameters. So first row, NMF2. Black line is what we start with. There's a root mean square errors for SEMI3. Sorry, for pi-array in comparison to SEMI3. And the root mean square errors reduced by half when we ingest our data. And the yellow line is when we use data propagation from one time frame to the next time frame, so-called Gauss-Markov scheme. But what's important in Anchor is that all of the parameters are being corrected. Sometimes when you use three-dimensional grid for data assimilation, you can see the change in mainly NMF2, but other parameters sometimes are not corrected. But what Anchor is good at, it corrects all of the parameters. Our paper was just submitted last week. You can find it in Space Weather, Anchor Global Parameterized Ionospheric Data Assimilation. Next, we worked on ingestion of slant total electron content data from ground-based station. And this data is more tricky. Why? Because ionosphere measurements and radioccultation measurements after Abel inversion are kind of like local measurements. You know where the observation occurred. But for total electron content measurements, it's just the integral of density along this long line, right? So you cannot point the place on the map where the observations occurred. So if your total electron content increased, well, do you just increase an MF2, or do you increase the thicknesses, or do you increase all of them at the same time? Nobody knows. And let me demonstrate this one simple example of how important this is for data assimilation. Let's say we start with the known truth. It's just one vertical electron density profile shown with yellow. We calculate our vertical tag, or the integral through this profile, and we call it a data. Then if we ingest this one data point into this blue profile, which we say this is the background, then the analysis, or the results of data assimilations, is shown with red profile. Let's now see how each parameter changed by this simple ingestion. Well, first column shows the vertical tag. The blue line, blue bar is kind of before ingestion, and the red bar is after. The smaller the bar, the better. So we improved in terms of VTech, but yeah, sure, we ingest in VTech, we ingest in the truth VTech. We're supposed to improve, yes. That's kind of given. Next, NMF2, the bar became shorter, which is good. It's kind of on the opposite side because it overshot, right? It became bigger than the truth. But it's still good because it's smaller than the blue bar. But next, HMF2 didn't change at all. By ingesting slant VTech, the data assimilation system changed just NMF2, but the HMF2 stayed on the same level as the background. But then when it became interesting, the thicknesses, we started with very short bar, but it became large for the top side, and same for the bottom side, and same for the E region and ME. So what it tells us is that if we ingest vertical tag or slant tag in a traditional way, let's say how ida4D assimilation does it. It can mainly improve only NMF2, but other parameters either stay the same or they become worse. And that's what we kept in mind for Anchor. So instead of this classical ingestion, we utilized the fact that our model is parameterized. According to IRI formalism, the slant tag can be calculated as integral from receiver to transmitter through the sum of all of the layers, sum of F2 layer plus F1 layer plus E layer. So we can use this equation to analytically find what the change to NMF2 should be to match the observed tag. Since only our F2 layer depends on NMF2, we analytically can perform this calculation. So to demonstrate this, please look at panel A here. So this data is shown for 1 ground-based stations and all GPS satellites for one 15-minute time frame. The black dots shows the observed tag. Then the red dots, no, sorry, I said it wrong. So the black tag shows the model tag. So this is the slant tag that's expected from the model. But red dots is what we made as an observation, as observed tag. So by taking into account the difference between the two, we can analytically calculate by how much the NMF2 should change to match this observed tag. And the next plot shows this NMF2. Again, we have observed NMF2 on the top and the adjusted NMF2, which is red. And you see it's very close to the truth in terms of NMF2. So then we have the collection of those points, and we ingest those NMF2 points the same way as we do ingest other parameters in Anchor. Okay, and here is the results for the S-tag ingestion. Again, we start with the background from the first panel, and since we know the truth, this is how the difference between the truth and the background looks like. So if it's very red or very blue, it means that our background is off from the truth. And after ingestion of all of those measurements, and I'm not showing them on purpose because there are operational locations, that's what we get for the analysis. So these are results of our simulation. You see how visibly it is close to the truth, so the truth is shown here. And now if we find differences between our analysis and the truth, they are way less in comparison to those ones. And the last panel just shows the residual. The closer we are to the zero line, the better. And we started with the blue distribution, and the distribution became very narrow. Okay. So now we can quantify those improvements in terms of root mean square errors. Again, this is for the whole globe. We start with the black line, as this is a root mean square of our background in comparison to the truth. When we ingest the ionozone data, the curve becomes lower, which is good, less RMSE. If we ingest only radio occultation, the curve is shown with blue line. If we ingest both ionozones and the radio occultation, it's a green line. But then when we ingest the GPS data, we go to the orange line. So the tag data from GPS receivers can reduce our root mean square errors on average by 41.6%, which is significant in comparison to other data sources. And when we ingest all of them together, radio occultation, ionozone, and GPS, that's where we get this final result. And that means the errors were reduced by 46.4%. So this is a very significant improvement, and GPS data has a great potential on improving our model. The results of this paper is unfortunately not available to the community, but they were submitted to DoD journal, so if you're a DoD or DoD contractor, you will see this paper there. And I would like to finish with tools for the community, right? So during this process, we developed PyRI. Again, code is available to the community. And I want to acknowledge Angeline for holding my hand during this GitHub training and all proper software release. Also, if you work with IRTAM coefficients, then we developed a tool that calls PyIRTAM. It allows you the processing of the IRTAM coefficients to construct the three-dimensional electron density very fast. Anchor code will not be publicly available, but if you would like to collaborate, please reach to me, Sarah McDonald, to Kate Zodi. And especially, we would like to ingest your data, so we will be able to share the results if this is the ingestion of either your data or publicly available data. That's all I had. Thank you very much for your attention.
Thank you very much. We have time for a quick question from the audience. Questions? Oh, there's one in Slido. Okay, so we'll have a question from Slido.
Okay, so this is anonymous from Slido. How this data set and the electron density maps are different from Cosmic 2 GIS data set? And parentheses, it uses IRI, Gauss, Markov filter, Cosmic 2, and GNS data.
It very depends on how they perform their data simulation. So all of the data simulation models in community, they kind of do the same thing. They combine data with model, but the flavors of all of them are very different, and the results are very different depending on those flavors. So yeah, I'm not sure how different their model is.
All right, thank you.
Thank you.
Okay, our next speaker is Claire Gask. Here we go. I like your title, by the way. It's not easy being green. So she'll be talking to us about leveraging detailed spectra and kinetic modeling for deeper insights into auroral and subauroral processes. Down this top.
It's fancy.
Yeah, it's kind of cool.
All right.
So have fun with that.
Great, thanks. All right. Good morning, everyone. Thank you to the CEDAR Science Steering Committee for giving me the invitation to come and talk to you all today. And thank you to all of my co-authors and collaborators for helping make this work possible. So today, first of all, I'm Claire Gaskoy. I'm a freshly minted PhD. I just got my degree a month ago. Thank you. I worked on several projects during the PhD. Today I'm going to share with you the one that perhaps I'm the most proud of, and also one that directly came out of a CEDAR conference. And I'm actually going to tell you that story at the end. But I think it's particularly fitting that I share this one with you today here. So without further ado, let's jump into the science. So this is It's Not Easy Being Green, for reasons that will hopefully become clear. And this is about how by combining quantitative spectra and also modeling, we can learn a lot about the physics of the upper atmosphere. All right, here we go. So the main topic of this is looking at Steve and the picket fence. For those of you who are not familiar with Steve and the picket fence, Steve is this purple or white arc that appears in the subauroral sky, so closer to the equator than the traditional auroral oval. And the picket fence are the green streaks of light that appear beneath it. These have only been part of the scientific literature since about 2018, so they're brand new to the community. And in particular, it is still a bit of a mystery where they come from, the actual process that is creating the emissions in this case. These were discovered by citizen scientists, so just photographers going out, taking pictures of the aurora. And when they first saw them, they thought it was just a new type of aurora, right? Lights in the sky, looks like an aurora, probably created the same way. But it quickly became clear that Steve in particular was something entirely different. You don't have the same particle precipitation signatures during Steve as you would during an aurora. And Steve tends to be co-located with very fast flows in the subaurora ionosphere called subaurora ion drifts. And so following that, folks thought it was likely, okay, that Steve is not created the same way as a normal aurora. There are papers on that. One of my co-authors, Brian Harding, has a paper with a theory of where the light from Steve comes from. That's not what I'm going to focus on today. Instead, I'm going to look at the picket fence. When folks looked at the picket fence, unlike Steve, it's green. It looks like a typical green aurora. And so early papers on the picket fence suggested that it was created by particle precipitation, just like the normal aurora. The problem comes when you look at the actual spectrum of the picket fence in detail. And so let me show you some of the discrepancies there. So first, looking at a typical green auroral spectrum, this is what it looks like. For folks that are not used to looking at spectra, there's a convenient rainbow on the bottom there, so that'll kind of orient you. So this is an optical spectrum of just a typical green aurora. And the main features that you see, a green aurora, right? Ooh, yeah, this is fun. So you can see that the main feature here is this green line. This is created by atomic oxygen, and it is the brightest thing. This is why the typical aurora here looks green. You also have contributions from the oxygen red line, and then this banded feature is from nitrogen. It's the nitrogen first positive. It's in the red. And then notably, you also have these features in the blue. This is the N2 plus. Okay, maybe this is harder than I thought. N2 plus first negative. This is actually from the ionization of nitrogen. And to get these, what's happening in the normal aurora, right, is that you have particles accelerated far out in the magnetosphere, precipitating into the atmosphere, striking the upper atmosphere, and then creating these emission lines. And each of these takes a different amount of energy to excite, essentially. So to get the oxygen green line, it takes about 4 electron volts. To get N2 first positive, it's about 7. To get that blue to ionize nitrogen and get that blue feature, it takes about 18 electron volts. But at the same time, in order for particles to precipitate and make it down to this part of the atmosphere, this is about 100 kilometers where these green aurora are happening, they need hundreds or thousands of EV to get down there. So essentially, whenever they're precipitating particles, you're going to get pretty much all of these features. So now let's take a look at the spectrum of the picket fence. This is what this looks like. So you'll notice the spectrum of the picket fence here. It's dominated by those green line emissions, right? You have very strong green line emissions. You have a hint of the N2 first positive, which you can see there. There's none of the red line from oxygen, but that's more or less expected because we're down at an altitude where that's very quickly quenched, so you don't get a lot of that. The suspicious thing is that you don't have any of that blue line from the ionization of nitrogen, which again, with particle precipitation, you would have. And so then this suggests that maybe this is not particle precipitation, maybe this is created by a different mechanism. So is it particle precipitation? Probably not. It is too green to be particle precipitation. And in fact, like I was mentioning, each of these lines have a different energy that's associated with the excitation. And so seeing this sort of constrains the electron population, which could be colliding with the neutrals to create this, to between 7 eV to create that N2 first positive, and about 18 eV, which would create that N2 plus first negative. And so this is not consistent with precipitation. The question we asked, right, was, okay, if it's not precipitation, what is it? Maybe there is something in situ, so right where you're seeing the light, that is energizing the electrons. At that point, there were a couple papers out that were actually looking at the structure of the picket fence, invoking different ionospheric instabilities to do so. Lynch et al. 2022 talks about the tearing mode instability, which is the same thing you get in rayed auroral arcs, which look a lot like the picket fence, at least in structure. The mission paper is looking at the ionospheric feedback instability, which is another instability, which when it arises creates low-altitude electric fields parallel to Earth's magnetic field. And the suggestion was that that might energize the local electrons and create the light in situ. So a completely different mechanism than the aurora. But no one had ever actually looked in detail at the spectrum and tried to connect it to that mechanism. So that was what we undertook to do with this study. The big question we're trying to answer, can parallel electric fields energize local thermal electrons and drive those picket fence emissions? So to do that, we were looking at a combination of data and modeling. The data is from the T-Rex spectrograph, which is the one we were using is up in Lucky Lake in Canada. We took spectral observations from the picket fence over the course of a single night. We were looking about 40 degrees above the horizon, so pretty close on the horizon, not directly at zenith. And the reason for that is we wanted our line of sight to kind of cut through the picket fence rather than integrating through it, because we weren't trying to figure out sort of the profile of the electric field, but we wanted to just look at a single point, more or less, of the electric field. And so we took these observations, we used them to look at the individual spectra, and from there, we looked at how much green line do they have, how much N2 first positive do they have, and we noticed that all of them, again, do not have any of that N2 plus first negative, none of the blue. And we looked at the ratio between the luminosities of the green line and N2 first positive, and then that ratio is what we sought to reproduce with our modeling. So then, can a model driven by paraelectric fields replicate that observed ratio while also not producing any of that N2 plus first negative? The paper has a lot more details about the kinetic modeling. I'm not going to get too far into the details here. But essentially, we took a realistic atmosphere. If you saw the talk this morning, part of that was the EMSIS model, building that atmosphere. And then we also used a model of the magnetic field in the ionosphere. We applied a parallel electric field to it of varying strength, and essentially saw what that would do to the local electrons. As you can see here, this is an electron energy distribution function, which for those students in the audience who might not know, it's essentially the probability that you'll find an electron at a given energy. So the black lines here are those for different parallel electric field strengths. And you can see that as you are increasing the strength of the parallel electric field, you are pushing the tail of that distribution function to higher and higher energies. And as you're doing that, the distribution function is starting to overlap with these cross sections to create the emissions that we saw. And so as you turn it up more and more, you're also going to be changing the ratio between the green and the N2 first positive. And if you turn it up enough, you're going to start to ionize nitrogen and get some of those blue emissions, which creates kind of a natural constraint on the field that you would need. At the end of this, so we didn't just use these distribution functions, we applied some additional chemistry to it. The paper goes into that in more detail, but I'm going to go ahead and skip to the results. So this, on the y-axis, we're looking at the altitude with that realistic atmosphere. On the x-axis, that's the parallel electric field. And what we're plotting here is the ratio between that N2 first positive and green line. And the thing to note is that observed ratio that we have fits very nicely on this plot. In particular, we found from this that at 110 kilometers, a typical picket fence altitude, we can reproduce that specific emission ratio that we observed in the picket fence with a parallel electric field between about 80 and 150 millivolts per meter. It's a high electric field, but it's not implausible. That is to say that this is a viable alternative to particle precipitation, and this is perhaps where the emissions in the picket fence come from. In the course of doing this work, we actually noted that there are several features in the aurora that have emissions that are similar to the picket fence. One of these is called fragmented aurora-like emissions. This came out in a paper by Dreyer et al. 2021. These look remarkably like the picket fence. If you look at the spectrum, they are also too green, meaning that they don't have enough, or they don't have any of that N2 plus first negative. But unlike the picket fence, this is on the poleward side of the aurora rather than the equatorward side. So it's possible that this is a similar driving mechanism. Another one is the enhanced aurora. So on the left here, this is kind of the regular aurora. The brightness sort of steadily increases as you get towards the bottom. But then if you look at the enhanced aurora, the difference is that you have this sort of discontinuity in the brightness. You have these layers that are brighter than other layers, and that can't be explained by particle precipitation, why there would be a brighter layer necessarily. Some modeling done by Thomas Carlson in 2005 suggested that those could be generated by parallel electric fields in the downward current region. Also within those, some spectra show that there is some N2 plus first negative, which you would expect because there's also particle precipitation going on. But there's not as much as you would expect from particle precipitation, which is to say that these layers, these enhanced layers, are also too green. And some early statistical work in 1985 showed that this could happen in as many as 50% of visible aurora that we see, which is to say that if this is the mechanism, it might be more common than we think. So I want to mention that that is kind of the summary of the work for that paper. There is a lot of ongoing work Brian Harding, Joanne Wu, and myself were recently awarded Living with a Star funding to study conductivity variations associated with Steve the picket fence and other subaurora phenomena. And in part, that's going to connect the model that we worked on here to the Harding model of Steve and some other things, so there's ongoing work there. I have an REU student this summer who's going to be doing a statistical study to try to understand more of the enhanced aurora, specifically looking at spectrograph data. And we've also recently proposed a rocket to attempt to measure those parallel electric fields within those optical phenomena for the first time, and are still waiting on a funding decision for that. I mentioned at the beginning that the origins of this work were from a CEDAR workshop, actually the 2022 CEDAR workshop. I had just finished my 3rd year of grad school when I was there. I met Reza, who's the second author of this work. He mostly has been working on TLEs, so sprites and that sort of thing, electrical discharges in the very bottom part of the atmosphere that we all study here at this conference, so up in the mesosphere, et cetera. And then Brian, who's done work previously on Steve, and we all essentially started talking just in the corner of the conference, on the couches when sessions were going on. We were just there doing back of the envelope calculations, trying to figure out some of this work. And essentially from there, we had notes, we sent them around, we kept the conversation going, and then it turned into this work. So for the students in the audience, I just want to emphasize that be open to different collaborations and ideas that come across. When I started this, I didn't know anything about atmospheric chemistry. Last time I took a chemistry class was sophomore year of high school. But this is all chemistry, And so just being open and willing to meet new collaborators, let the puzzle pieces fit together, and see where the work takes you is really, really rewarding. So thank you to I swear the CEDAR organizers are not paying me to say this. But thank you to the organizers, thank you to everyone here. Here's the summary of this work. If you want more, you can check out the paper, and I'm happy to take questions. Thanks.
All right, thank you very much for that story. That's exactly the type of stuff we like to hear. We have time for a question from the audience. Caitlin.
This is not my field of study, so this might be an ignorant question, and maybe you covered it, but what would cause those intense parallel electric fields?
Those are good questions, or that's a good question, and it's still something that we're working on. The modeling paper that I mentioned in the Carlson paper looks at how the fields might arise due to essentially having to close the currents in the downward current region. That could cause the field to arise. But I think more electrodynamic modeling needs to be done to really understand it. The common wisdom, right, is that you can't have a parallel electric field in the ionosphere because it's just going to short out instantly because of the high parallel conductivity. But the idea is that down in sort of the collisional base of the ionosphere, where the parallel things would try to move along the field, but they would collide with the neutrals before they're able to completely short out the field, you might be able to sustain these kind of fields.
Okay, so I believe Mark? Oh, Mark and Angeline are now going to talk about the CEDAR bylaws, I believe.
I'll just speak for me. All right, well, thanks, Matt. We're running a little behind time, so I'm not going to talk about the code of conduct again, other than to point out the importance of it and that it's out there. However, I do want to say that when I started out as CEDAR Science Steering Committee Chair, I had no idea what I was supposed to do or what my responsibilities were, what I could do, what I couldn't do. And so Angeline has taken the lead in putting together a set of bylaws to sort of record how CEDAR operates, what we do, what our purpose is, and how things are done. She spent the last year or so working on that with help from the rest of the CEDAR Science Steering Committee. So I think Angeline will present the first draft of our bylaws. We haven't formally adopted them yet. We're presenting them here for people to look at, and I think we will vote later this week on the steering committee as to whether we will adopt these as written. It's a living document, so we'll be able to modify them, but I think it's really important that we have a set of bylaws written down, and I'll let Angeline walk you through it.
All right, as Mark said, CEDAR has existed for a very long time, but without a set of documents that record the institutional knowledge and provide a level of transparency between the general community and the people who are currently running things on the CEDAR Science Steering Committee. So before I came on, the CSSC decided that it would be good if we knew what was going on, and when new people came on, they knew what those roles were. So I was tasked to write things up. So here's an outline of what is included in the bylaws. I'm going to briefly go over what's in each of these sections. Obviously, this is a very condensed version of what's written down in the documentation, but I've included all of the important bits. So first, who are we? At CEDAR, we're a group of people who have an interest in the neutral and charged portions of the lower and upper atmosphere. And we investigate this using a variety of methods that include observations, models, experiments, and theory. Our purpose is to advance the science objectives in the CEDAR program, to provide a forum for exchanging ideas on these topics, to promote CEDAR science to other stakeholders that include the general public, scientists outside of the USA who are working on the same things, and the government. We also conduct workshops to advance the state of CEDAR science. We promote discussions of programmatic issues that affect the daily lives of all of us at our institutions. And we provide a means for the CEDAR community to communicate their thoughts to the stakeholders in the government and in other communities like GEM. Finally, the role of the CSSC within CEDAR is to contribute to building a healthy scientific community where we can all thrive. So, membership, who's a member of CEDAR? Everyone here. But we've defined this very broadly to be anyone who has an interest in our science regime, regardless of where they live, what their current employment status is, or anything else. As a practical measure, we've defined active members as those who are subscribed to the CEDAR mailing list, which you can do for free on the website if you haven't already. The CSSC is a board that consists of a chair, several committee members, 2 student representatives, and then different liaisons that provide perspectives from different interested groups. We currently have a GEM liaison and an international liaison that wear the double hat of full committee member, but work to provide us perspectives from these important communities. We also have NSF liaisons who are not voting members, but provide a direct line to provide the CSSC with information on research funding and workshop funding so that we can continue to provide all of the resources that we've promised to the CEDAR community. Committee membership is 2 to 3 years, depending on your position, and rotates regularly to ensure that we always have perspectives from different members of the community. I've mentioned the CEDAR mailing list before. It is human moderated to ensure you don't get large quantities of spam, and is what we're using to provide define our active membership. The CEDAR workshop in the bylaws, we have sections that cover several aspects to ensure that you have a consistent experience here. We talk about providing student support, student tutorials, grand challenges, different CEDAR programmatics, science highlights, and community-led science. The programmatics ensure that you get reports from the different relevant funding agencies, that we provide awards and recognition, and reports from the DEI task force and other important elements. The resources that we work to provide, again, are career awards, several of which you've witnessed today. We have awards that span every stage of career, from student awards from the posters to the distinguished lecture. Apart from the student poster awards, everything will be nominated, available for nomination by the community. And you can find out how to do that on the website. So we encourage you, if you know someone who you think should get an award, fill it out for next year. The additional resources we supply, apart from the workshop, are the website, the demographic survey, and then informal community discussion forums that are less formal than the mailing list, to provide people an avenue to continue discussing and meeting their colleagues throughout the year. Currently, we have a Slack, we have a YouTube channel where you can see a lot of the talks given here, and then there's also a group on Facebook. Finally, as Mark mentioned, this is a living document. You can bring amendments to the bylaws as a normal community member of CEDAR, and if that is done, then there will be a vote amongst the community on whether or not the changes should be adopted. In this way, the entire community has a say in how our community is run, and it won't be a top-down discussion about how things should go. All right, I'm going to hand things back to Mark. This is it. Oh, one more note. I did adopt these off of the UK MIST bylaws and by looking at the GEM bylaws. So all of these have worked successfully in communities similar to ours before.
Thanks, Angeline. Again, I said I really appreciate the work that you and the other CSSE members have put into this. I think we have time maybe for one quick question, if there is any. I think we have the bylaws posted now, Ling. Is that right? The bylaws can be seen as written on the website now. Is that correct? Yeah.
I'm not 100% sure. The code of conduct is.
So we will today make sure that we have a copy of the bylaws available for you to look at. And as I said, I think we want to formally adopt those later this week. So let's see if there's no further questions. I guess I'll hand back to Matt.
Alrighty. So the next section of this session, I'm going to turn that off so we don't get feedback here, is a panel on the Grand Challenge workshops. So if you've been at CEDAR the last few years, you'll know that we have these sort of persistent Grand Challenge workshops that last for a few years. So our moderator for this is going to be Sue Feng, and then we have panelists for each of the 3 Grand Challenges that are currently going right now. So I'll call you up here, please, if you're a panelist. Come up and sit in the bright lights here in front of everyone. So Jens Oberheide, Matt Jones, Titus Ewan, Jonathan Snively, Lynn Harvey, and Aaron Ridley. Please come on up. So I'll let you manage the rest.
Let's see how that goes. This is my seat. So I suggest to the committee, say, you know, we always have talks, and you're going to see a lot of talks this week. So why don't we try to do a panel discussions? Because I have a lot of questions from students asking me why we do all of this and how does it connect it to each other. So the format today is going to be, let's try it out. And if it's horrible, just let me know. We'll feedback to the committee. So the format is going to be, each team will give a short talks, and we'll give Jens a little bit longer since the first year of the challenge session. So, and the rest of the team will get about 10 minutes. Then we'll have a few questions, Q&A session, and I ask them to answer the question in a short format. We'll hopefully they don't give an hour chat. And then the only question are allowed is through Slido. You're not allowed to raise your hands and use microphone because we want to make sure we can all eat lunch on time. So let's see how it goes. And first talk, it will be Jens Arbor. Let me read out the sessions. So each Grand Challenge sessions got 3 years continuous discussions, and each year in CEDAR they get two-hour slot. So the first one is impact of the terrestrial weather on the space weather of the ionosphere-thermosphere, mesosphere.
Thank you, Zove, and thank you to the CSSE for selecting this new Grand Challenge workshop on the impact of terrestrial weather on the space weather of the ionosphere, thermosphere, and mesosphere. And so I'm giving this introduction here, this overview about the workshop on behalf of the convener team. So why this new Grand Challenge workshop? So our overall objective is here in bold, advance the understanding of whole atmosphere interconnections between terrestrial and space weather through combined modeling and observations across different spatial and temporal scales. And so you see this highly emphasizes coupling, which is kind of at the heart of what we do at CEDAR, basically from local scales to global scales, from the neutral atmosphere to the ionosphere. And I mean, it's not really new to look into terrestrial weather and upper atmosphere ionosphere coupling. And as we all know, we really made some progress, at least in the past years. But I think we probably all agree here that still very significant gaps in our current understanding of the whole matter here remain. And I mean, this has been, fortunately, I must say, realized also by the federal agencies. So NASA, through the LWS program, has a focused science topic that looks specifically into this matter. NSF, through the Answers program, has addressed through a couple of new projects this question. And also on, at the international level, there was a very recent workshop from ISI in Bern. Also historically, Geospace has always looked into weather-space weather connections. And so the idea here for this whole Grand Challenge workshop is now to basically join forces with the broader CEDAR community, really to really make use of all the synergies we have to really dig into all the potential from particularly the ground-based observatories to really enable a transformed view of how terrestrial weather impacts the space weather of the ionosphere and thermosphere system. And lastly, I think this will also be a useful thing to better define, more clearly define the state of the art in the light of the new upcoming missions, EASY, dynamic, and hopefully also GDC in the future. And so the specific goals of this workshop are to reveal the critical links between weather and space weather, basically through 4 different broad topics here. So the first one is really to define the observational and modeling baseline data set, what we have. So what do we have? And we need that to better understand what is really missing, what additional things cadence-wise or observation-wise do we need. And then use basically these baseline data to develop a set of metrics to enable a more quantitative evaluation of data model comparisons, to really go beyond, this is my observed curve, this is my modeling curve, and there's good agreement. So what's really the more quantitative measure, perhaps even thinking along the lines of how in meteorological weather forecasts, the quality of a model or modeling forecast is really quantified. So can we actually do that in our community, and to what extent? And then third, to evaluate the state of the art models, or in particular, all the new high resolution models that become more and more applied to our field, and use that to really look in a more quantitative way into the impact of data assimilation. So in a way, also to use the models, what kind of data, what cadence, what location, what parameters, state parameters do we really need to do a better job than what we do right now. And finally, of course, we are all scientists. I think that's quite obvious. We want to look into the physics behind that and how things really work, so the physical mechanisms. So, and in the following, I basically want to show you a few examples, basically walking you quickly through different scales, spatial scales, temporal scales, what we have and what we are looking for, to give you a kind of an appreciation of how weather can really impact the space weather of the ionosphere and thermosphere. I would like to start more with the smaller, more local scales, acoustic and gravity waves. So this is an example from a very recent paper from Pavel Inchin and co-workers. I'm not even sure if the DOI is already online, but the paper is accepted, so it's a brand new thing here, which basically shows how continental scale weather directly impacts the space environment. So that's basically 3 maps. The left one is tropospheric wind fields, color-coded. That was this big winter storm in the continental US in December 22. I still remember in South Carolina, we of course lost power, and it was really lousy cold for a few days, so I will take a while until I forget that. And so the center one is how the stratosphere reacted to that. So you're basically looking into the upper stratosphere, lower mesosphere, so through the wind fields, in particular over the Rocky Mountains and so forth. A lot of gravity waves were triggered, which you can clearly see here. And on the right, finally, the ionospheric response in electron density here around 250 kilometers from the ground-based GNSS data. And so clearly on a continental scale, severe weather, winter storms make a lot of, cause a lot of variability in the ionosphere. So it's not only the continental scale weather, but also more localized severe weather system here. That's an example for a severe thunderstorm or deer echo, which are the really nasty ones you want to get out of the way. So the top one is, the top row are observations against ground-based GNSS data in VTEC here. And in the lower row is a combined MAGIC Gemini high-resolution modeling. From Shantanap and his co-workers. So the greenish plots are how the neutral thermosphere reacts to the thunderstorm-generated gravity waves, and the blue figure is how the ionosphere reacts to that. And the take-home message here is that the current generation of high-resolution models actually do a pretty amazing job in reproducing how the real world really looks like. So now moving on to more mesoscale and global scales. So this is an example actually from my own group, from my own previous students and my current student, that basically looks into how atmospheric tides react to recurring tropospheric weather events. And the example here is the so-called Madden-Julian oscillation, which you see in the left. That's basically kind of a 60-day oscillation in tropospheric convection and rainfall rates, which you see color-coded there. And we already know that the modulation of tropospheric convection has a big impact on the neutral tides in the E region. That's basically what you see in red there. That's basically a tidal modulation in this 30 to 96-day range of a particular tidal component. And in black overlaid is actually the F region electron density response from cosmic 2 data at 15 degrees magnetic latitude, which basically means that the E region dynamo modulations that can basically conclusively track down to the Madden-Julian oscillation really impose a corresponding modulation in the F region ionosphere. And these are normalized data, but to give you kind of an appreciation, the magnitude of the electron density modulations is about 30% of the monthly mean tides, or if you compare that to the background ionosphere, we are talking about 3 to 5% roughly. So this is a result from another student of mine from Mukhtar. She basically used the latest tools we developed in data analysis to quantify tidal wave energy fluxes on a global scale from the lower atmosphere into the upper atmosphere. So really in an attempt to more quantify the vertical coupling we always talk about. So what's really the amount of joules we put from the lower atmosphere into the upper atmosphere, and corresponding work can also be done for the momentum flux. And these are global annual mean on the right, and that basically shows you at what altitude range the diurnal tides dominate. That's only a tiny little region in the upper mesosphere, and it's largely all dominated by semidiurnal tides on a global scale here. So then moving on to mesoscales, these are very recent high-resolution vacuum modeling results from a paper that Han Li and co-workers wrote. So color-coded is the momentum forcing for zonal and the zonal and meridional momentum forcing for mesoscales. That means 2,000 kilometers or less. Overplotted are the resulting wind fields, and perhaps the real impact is on the right here. You basically see that the high-resolution modeling, and that I should say this is the new high-resolution version of WACCM. You see that the whole O to N2 thermospheric composition really decreased on a global scale because the thermospheric circulation changed. And this now compares much, much better with GUVI observations of O to N2, which also shows actually how important thermospheric composition measurements are, not only for the friends of composition, but also to see how thermospheric dynamics really works. And finally, intra and interannual scales. So on the left column are SABRE observations, right column are WACCM simulations from Valerie Yudin. And this basically looks into how the stratospheric QBO, so quasi-2-year oscillation, impacts the upper atmosphere here, looking into the semidiurnal migrating tide. And the important point is here in the bottom. If the QBO is in its east phase, that there are actually more pronounced sudden stratospheric warmings and also an enhancement of the semidiurnal migrating tide. So on an interannual scale, the QBO has many more impacts. This is an example from Larisa Goncharenko and her postdoc Dupinder Singh that basically developed a new empirical model of NMF2 for ionosonde data. And this new model basically enabled to really identify now in ionosonde data a QBO signal that could be analyzed, which you basically see here. And the lower row are wavelets that see this very pronounced 2-year signal here. So basically, it's not only the tropospheric weather, but also the weather of the stratosphere, if you want to call it that way, that maps into the ionosphere. And this is the last science slide here. That's the impact of data assimilation on model performance. And this is what Manbarat Dudley did. That's basically checking different WACCM versions versus mighty wind observations. So color-coded as standalone WACCM versions and MERA2-driven WACCM, so SD WACCM X. And then in orange, the WACCM X Dart version, which basically uses also mesospheric data for data assimilation. And you see, so this is basically compared against mighty wind observations along track to look into systematic biases here. And you see that the results are kind of mixed where we stand right now. So for the meridional winds on average, it's kind of similar in no matter what version of WACCM we really use. For the zonal winds, it's different. So I mean, during daytime, the standalone WACCM seems to do the best job, but during nighttime, actually, the data assimilation WACCM Dart does a better job. So why is that so? How can we really make these kind of things better and so forth? That's part of the current challenges, I would say. And so this is the timeline for the Grand Challenge workshop. So this year we basically want to look closely into what data do we have, observational baseline and modeling baseline. Next year, we want to or plan to look more closely into data model comparisons and the impact of data assimilation, and then finally talk more about the physical mechanisms there. So we have 2 sessions for that. You see the times there, and then I leave you with the speakers and the general topics that we cover today and on Wednesday. Thank you.
Okay, now we have the second group that is going to talk about the, I think Titus, yeah, the role of gravity waves in the mesosphere, thermosphere, and ionosphere, cross-scale coupling, and irregularities through observations and numerical simulations.
Hello, everyone. Good morning. So first of all, I'm probably the only GC chair in the CEDAR history that is not expert on the topic he or she proposing. So the GC is heavily rely on my co-conveners. So these are the institutes and co-conveners of our GC team. Thank you very much. Okay, so we know gravity waves are everywhere in the atmosphere, especially in upper atmosphere. They're very highly active. Oops, so how do I? So how do I move it?
Yeah, tap button and point at the monitor.
Oh, here. So this is the high-resolution vacuum X free-run simulation of gravity wave propagating throughout the atmosphere. This is the temperature perturbation at about 87 kilometers. The altitude is chosen because the upcoming the ongoing mission of all, specifically looking at the 87 kilometer small-scale gravity wave activity. So, last year, Jonathan gave an excellent overview of the model developments and experiment observation over the past few years, highlighted the most recent model results and the observations. As for the generation and propagation of the gravity waves, I borrowed these slides from Sharon Vada's talk. It shows the complexity of these processes. You can see the, okay. You can see the sources of gravity wave generations in the lower atmosphere. Including the orographic sources, mountains, and also convection sources due to severe weather events. And and we also emphasized that the higher order gravity waves are also important, especially in the IT system, because and these secondary and tertiary gravity waves are generated through the gravity wave dissipation and breaking in the middle atmosphere, and they actually are highly active in the IT system based on the models. So these higher order gravity waves are important to be included in the model development. And of course, you have aurora-generated gravity waves, and the heavily investigated Tonga volcano eruption also shows the gravity wave generated in the at the surface of the Earth, but they actually impact the ionosphere above. All right, so I'll just keep talking. Let me think. Let's see, what's next? Okay, so basically, over the past decades, that we have learned a lot of gravity wave dynamics, its principle, and its. Oh, okay, good. Just the middle one. All right, I remember that. So the theories and observation that we obtained over the past few decades have enabled the models to relatively reasonable gravity wave perturbation in the atmosphere, from middle to upper atmosphere, for both GCMs. So this is the GCM. Okay, I need to stop using this. GCM and local high-resolution regional models to reproduce these observations and generate and the potential impact of these gravity waves in the middle and upper atmosphere. Okay, so that actually brought up an opportunity. So because we learned a lot over of this physics and chemical principles of gravity waves, and can we extend all these principles and results to understand the whole IT system, whole ITM system? So this is a slide that I borrowed from Jonathan's talk. So the observation so right now you probably learn this, already know this. Most of the observations and numeric and the physics principle that we learned is derived from the mesopause region. So can we extend it to the ITM, the whole ITM system? One of the test base is the Mango network that shows that measure the gravity wave activities in the mesopause region, and also have gravity wave observation in the thermosphere. So this will be a great test base for all these physics principles and the results that we learned over the past decades. And adding to our arsenal is the machine learning technique that's just developed over the past few years that actually can reduce the complex gravity wave simulations, the time of complex gravity wave simulation significantly. So this is the paper highlighted by the JRL, using machine learning techniques to simulate gravity wave and KHI instability. Over the past several years, we start to have lots of ionosphere observations that shows the gravity wave signatures. So another opportunity that we have right now is, can these new ionosphere observations advance our ITM dynamic understanding? So this is a movie. Oh gosh, movie. How do I? Okay. Oh, good. So this is a movie that shows the large-scale TIDs, and also they show some wave-like features like MSTIDs. So, and these MSTIDs could be the results of the gravity wave propagating from below or generated in the middle atmosphere. So that actually, okay. So this is also, of course, the famous picture of Irfan's work of a TITC map showing the concentric gravity wave signature during the storm, during the thunderstorm or hurricane, I forgot. so that also shows that these TEC results can also help us understand the ITM neutral dynamic, which is the new aspect of our investigation. And again, the Tongo volcanic eruption provided a unique tech space to test all our knowledges. And because we not only see the gravity wave and the acoustic gravity wave near the surface, the middle atmosphere, upper atmosphere, we also see its signatures in the TEC map. And also the numerical simulation shows that the secondary gravity waves are also generated in this volcano eruption. How much time do I have? Oh, okay. So I can see. Okay. So the left plot shows multiple satellite imaging of this gravity wave generated through after the volcano eruption, and we have observation from the surface. Okay, so I'll stop you. Okay, from the surface all the way to the upper atmosphere and ionosphere, and the left and the right plot is the numerical simulation. And another exciting news is the ALL mission, specifically focusing on small-scale gravity wave and its impact in the ITM system. The instrument was successfully launched and deployed on the International Space Station last November, and starting to take data. So this mission is actually fits well with our GC objectives and goals. We are really looking forward to the new results from this new mission, from this ALL mission, and we have a talk about the upgrade. Of the ALL mission and its update in this afternoon. So there will be I'll be very exciting to listen to. Okay. So this is the plan of our GC session from year 1 to year 3, and in year 2, our goal is to address the couple of scientific questions. How do various scale of gravity wave couple into and change the ionosphere and thermosphere regional state and variable evolutions? So we actually have a few specific talks on these topics, and also we want to want to answer what is the best and most efficient operation mode for the existing local instrument cluster to address the small-scale wave effect and contribution to GCM. So right now, most of the small-scale gravity wave observation and investigations are based on local or regional observations. So it will be extremely beneficial to the whole community to see how we can use these local and reasonable results and contribute to the GCM developments. I think that's, Yeah, that's, oh, so this is the agenda of year 2 GC. The Monday, oh, excuse me. So it's the Monday and Thursday sessions, so please try to participate.
Thank you, Titus. In the third session, unfortunately, the main convener, Yueden, cannot be here today with us. So Ling is going to give a brief talk. The session is Inter-Hemisphere Asymmetry and Impact on the Global IT System.
Yes, thank you for giving me this opportunity to give you a brief overview of the Grand Challenge on Interhemispheric Asymmetries. This Grand Challenge is now in its 3rd year, and you should be receiving a detailed presentation with lots of rich science highlights that I think is going to be postponed till next year that you'll get from Yue. She regrets that she's not able to be here. She had a family emergency, and I found out last night that I was going to have the opportunity to talk with you, and so I threw together just a few quick slides. We'll probably make up some time here to give you a flavor for the Grand Challenge and hopefully inspire you to attend the sessions tomorrow and Friday. So you can see the title, the conveners that have been working to organize the sessions over the years, myself, Yue in large part, Xingyu Zhu, Yunju Chen, Astrid Mata, and Aaron Ridley on the panel here. The justification for this Grand Challenge has been that interhemispheric asymmetries exist in both the ionospheric and thermospheric, neutral and plasma, different phenomena, the particle precipitation, conductivity, auroral patterns, so on and so forth, as well as in lower atmosphere properties, in large part because of the interhemispheric asymmetries in the polar vortices, which are ultimately tied to the fact that in the Antarctic you have a continent, and in the Arctic you have an ocean. So the stronger polar vortex in the Antarctic filters waves, gravity waves, planetary waves, and tides differently. But there are also interhemispheric asymmetries due to magnetic field geometries in the solar wind, and so on and so forth. The temporal scales range from hours to seasonal, and interhemispheric asymmetries arise both from forcing from above in magnetosphere-ionosphere coupling and from below in the upward propagation of different waves. So despite the fact that interhemispheric asymmetries are ubiquitous and that they likely have important implications for space weather, their properties have not been documented, and they are not input into models, so this prevents simulations that study their impacts on the global ionosphere-thermosphere system. The goals of the Grand Challenge have been to document, first and foremost, the interhemispheric asymmetry characteristics. When do they occur? What latitudes? What local times? What seasons? In what phenomena? Determine if the interhemispheric asymmetries are different during quiet and storm times. Determine their significance on magnetosphere, ionosphere, thermosphere system and space weather. Better understand how they're forced from both above and below. Input interhemispheric asymmetries into models and quantify their impacts. And then identify difficulties to measure interhemispheric asymmetries and how these gaps might be closed. So there are also interhemispheric asymmetries in observations themselves, and those may map onto sampling phenomena differently in the different hemispheres. How do we account for that? This Grand Challenge has synergistic efforts with other ongoing activities. One is Living with the Star focused science topic entitled Causes and Consequences of Interhemispheric Asymmetries in the Magnetosphere, Ionosphere, Thermosphere System, led by myself. And Titus, I don't think that you're the only person that is involved in a Grand Challenge where it's not exactly my area of expertise. but I represent a team that looks at the interhemispheric asymmetries in upward propagating waves from the neutral atmosphere. We also have PIs, teams led by Yoonju Chen, Anthea Koster, Hyomin Kim, Naomi Maruyama, Astrid Mota, which their team has now been handed off to Gang Lu due to a shift in organization, and Kevin Pham. So this is a really broad Living with the Star focused science topic that spans basically from the troposphere all the way out into outer space. This grand challenge is also synergistic with the NSF GEM focus group led by Hyomin Kim for the last 6 years on interhemispheric approaches to understand MI coupling, and as well as an ISI team also led by Hyomin Kim and others to understand interhemispheric asymmetries and MIT coupling. So last year we had 2 sessions, and we started off with 2 invited scene setting talks, one led by Gang Lu, the other by Katrina Bossert, covering interhemispheric asymmetries in top-down coupling and forced by bottom-up coupling. And then we had a host of lightning talks and had time for a lot of discussion. We're going to have the same kind of format this year. In our second session, we had Dolores Knipp and Chuan Gan speaking about different aspects of interhemispheric asymmetries in both field-aligned currents, pointing flux observations, and in the GOLD observations, and then also a variety of fast lightning talks, leaving time for discussion. So tomorrow we have a session, and Erin Ridley's going to give an invited talk updating on the MAX satellite mission. And Cesar Valladares is going to give another invited talk on observations of interhemispheric asymmetries and post-sunset equatorial ionosphere anomaly during strat warming events, followed by 8 lightning talks and leaving time for about a half hour of discussion where we can all interact. And Astrid Mota has come up with a number of important questions that we can talk about to guide the discussion. And then on Friday, we'll have another session in the late morning with Erich Becker giving an invited talk on interhemispheric asymmetries and multi-step vertical coupling and primary and higher order gravity waves, followed by a talk by Ying Shi and interhemispheric asymmetries and magnetic field residuals. Then a handful of quick, exciting lightning talks and another 30-minute discussion. So I hope to see you all tomorrow and Friday in our sessions. And stay tuned next year for a really great talk by Yue, where she'll give science highlights over the last 3 years for this grand challenge. Thanks.
Does this work? Oh, worked. Okay, thanks, Ling, for a quick update. So here's the questions, right? So I work at Space Weather Prediction Center in NOAA. So in real world scenario, we interact with the customers directly and users. So they want to know what's going on in neutral atmosphere. They want to know what's going on in ionosphere in real time. They want to know what's going on tomorrow, what's going on in forecasting mode. So their application, including GPS specifications. They also want to know the HF communications. They want to know satellite drag. Now they want to know how to re-enter their rockets. So I think there are a lot of requirements. I just want all of you seeing that whatever you're working on actually have a real world applications, and they're all connected, right? You just heard that the ionosphere changes associated with thermosphere changes, and thermosphere is very determined by the gravity waves and MLT dynamics. So how is your work? And I'm sure everybody in this room, you contribute to the system in a certain way. So here's the first question I have. I mean, we see in that short half an hour, there's so many tools, there's so many observations. So I want to ask our long-term members in the community and prestige scientists right here. So how do we better integrate all the tools and the methods that we already developed, right? So how do we get to a better way so that we can improve our knowledge right now? I just think there are a lot of tools like scatter, things are a little bit not integrated in the way that should be. And maybe we don't want to. So what are your thoughts on that? If anybody want to share some thoughts?
Okay, so I guess I qualify as a long-term member of this community by now. It's, so, I mean, obviously, this kind of gathering and the Grand Challenge workshops are one approach to do that. But I think we also have to be realistic that this involves a lot of real work, and real work also costs money. That's, I think to really do a better job in integrating tools, methods, data, and so forth, what we have, focus team efforts that come out of, let's say, things like the LWS program through the focus science topics, or NSF answers like programs. I think that's the kind of way to go, in my opinion, to actually have the resources available and very different expertise of people from different institutions that really work together to integrate what we already have.
Thanks.
So I'll add an item from a modeler's perspective. I think there's a very practical aspect of this question too, and simply speaking the right language between tools and components in sort of the models and data that we use to do our science. So in terms of being compatible, I mean, there's a need to have a community awareness of standards that are going to be acceptable to the potential future users of it down the road. I think even if you're on the basic science side, having an understanding and appreciation of the directions as to where things might go in the future is helpful, because it improves one's efficiency in doing work. Science, I think, is slightly more efficient when we're speaking the same language with regards to how we're putting things together in terms of data standards, or at least being aware of how one could do that with a mind for the future. So.
I guess one of the things I think of the CCMC when we talk about these types of things. Like, I, as a model developer, basically just put my model out there, and then CCMC, or people who use CCMC, run like all of these different models, and then they do comparisons between them. And I think of sort of the ultimate as like the hurricane forecasts, where, you know, they want to know where a hurricane is going to hit the United States or wherever, and so they run 15 different models for 5 days out, and then they come up with sort of an ensemble prediction. And I envision that we will eventually get there with, you know, everybody has a different model, and some higher level place will run these different models and will come up with ensemble predictions. And so I envision my role as a model developer just to develop the model, and then some higher entity to take that model and use it combined with a bunch of other models to do something greater than myself.
It's interesting to hear that, you know, code, you know, standardization of the code, and then everybody can use it and provide information in a quick and rapid way. It'd be great.
So it's so cool, all the work that people are doing. The talk that we saw earlier on data assimilation of observations in the ionosphere, I think we need to just continue on course, right? And then, so to do that, we need to continue to acquire great observations, right? So that's one thing, you know, launch these magnificent missions that we've, you know, had in the pipeline and that were mentioned in the decadal survey, GDC and Dynamic, to provide the observations to the models, have the modelers continue to assimilate those observations, the Aussie experiments and data assimilation techniques that are being advanced. Like Aaron said, you know, numerical weather prediction in the troposphere, you know, it is so far ahead of where we are in the ionosphere. We're like 50 years behind because we haven't had the observations. And so I think we just need to continue fighting for the satellite missions that we need in order to then improve the models and assimilate those observations and get the models, you know, representing all the physics that are going on, and perform the experiments. And I think that we're on track. I think everybody's doing a great job. Just need to keep going.
second what Lynn just said. I mean, I think we're starting to move to as we saw today with our talks, we have observations. Okay, now what version of our model, what versions of our models compare well against observations, independent validation, and also what observations do we actually need? We know that there's a big gap in the thermosphere in terms of the observations that we have, right? It's a data sparse region. But what ones will give us the biggest bang for our buck? Which ones can we use to actually improve our forecasting? I think that's where we're headed to. And that's the importance of missions like GDC, like Dynamic, and then being able to, again, go back and do these reanalyses and see, okay, are we doing better with just this one measurement? Or do we need 2 measurements? Do we need 6 measurements? Do we need temperature, winds, et cetera? These are all the things that we're doing and moving towards, and I think we just have to keep pushing forward.
Want to add something?
So you identified a really important point. There's a lot of value to often doing some of the modeling on a, for example, OSSI basis before actually collecting the data. And having an initial basis is extremely strengthening to know what to do next with regards to data collection. So that's a great point.
Yeah, one of the best papers that I've ever read on this, I'm going to call somebody out. I think Alex Chartier did a paper where he basically tried to say, like, what is the thing? If we want to understand what the ionosphere is going to do in 24 hours from now, what is the most important data that we can assimilate right now? And thermospheric composition was the most important thing to assimilate. And we have no thermospheric composition data at all. So
yeah, they just answered all the question I had already in all my question list. So, I actually agree with all of you, but I actually want everybody in the audience to think about it, right? So we interact with space industry. The question to me is, if you get all my data, what are you going to do? If you get all my magnetometer data, what are you going to do? I'm talking about Starlink, right? If you get all my rocket data, what are you going to do? If you get all my stuff, what are you going to do? And we all know there are not scientific grade of data. So what do you want to do? And I want you to come talk to me and tell me what we should be doing with those data. And that's just different-centric of where we are going, right? So I think I'll just leave a question for audience. Any audience question coming up?
There is a question. The question is, do we have enough data from various instruments to be able to quantify the energetic inputs from the lower atmosphere that affect the ionosphere?
Yeah,
So
no.
the short answer,
I think we need global 4 to 6 times per day measurements of temperature and neutral winds at spatial resolutions sufficient to quantify gravity wave activity and tides, and we are far from that currently.
And I also want to point out that we need a new innovative approach to measure all these species or parameters that we've been missing over the past few decades. So far, all the measurement techniques and the principles were developed 30-something years ago. So we really want, like I said, a new approach to be able to measure all these new critical parameters.
So
go
ahead.
So, like Lynn already mentioned, the next real quantum leap, in my opinion, will come to actually have concurrent dynamic and GDC measurements. I would argue that probably 99% of people in this room would agree with that. But even if this is not really my particular expertise, I would also like to keep or like to make an argument that, particular for NSF, that's really crucial in my opinion to maintain the in-current scatter radars and to further expand the in-current scatter radar network in particular. So I mean, we don't have really any noteworthy ISR capability in the southern hemisphere. That's in particular in Antarctica, and I think this is a big gap in terms of what we should actually measure in being aeronomers.
So one of the things that I find interesting about this question is also addressing the data sources from other folks' systems, for example, descriptions of tropospheric weather on a global basis sufficient to be able to describe the inputs to the upper atmosphere from below. And that's a really tricky problem, especially if you're looking at basically dynamics over the ocean as opposed to over continents. And one of the trends that we've seen is being able to use data, of course, where you have it to the greatest extent possible to know how much you'd be able to sacrifice if you were trying to do an accurate, for example, regional description of dynamics offset from a place that had really good existing data coverage. So there's sort of a laboratory perspective, especially that comes into play with gravity wave science, with understanding dynamics where you have a lot of focus measurements in one place, and then understanding how you could constrain the environment with maybe a lot less data somewhere else. So that's an interesting learning process that's, I think, been taking place in recent years.
Well, going back to John Emmert's talk this morning and Aaron's comment about composition, thermospheric composition, one of the things we've kicked around with MSIS is providing a output that would tell you where there is data and where there's not. So when John shows a plot of NO data and you look at the coverage, you think, wow, that's great. Actually, between like 100 and 200 kilometers, where all these upward propagating waves are dissipating and changing the weather of the day, we have very little observations. Very little observations. And so measuring that region of where this energy deposition is actually going into the system and then influencing the ionosphere above it and locally is something that we severely lack. And so I would make a very quick answer to that question would be no, especially when it comes to atmospheric composition.
Cool.
Thank you. Any more questions?
There's two more questions from the audience. So I think it's one of the questions is a follow-on, so I will ask this actually submitted later. A step above from what do we need to measure, how should the community present the why does it matter past the space weather fear-mongering?
I have a lot of customers who need our stuff, so I want to make sure that, I think maybe I shouldn't be asking questions, but we do get questions on, give me the density at 80 to 90 kilometers. Give me the wind at 400 kilometers. Give me the ionosphere density. Give me the ionosphere TEC. Give me the things in polar region. How do I know my rocket is going to be okay when I fly through the areas? So I think there is a real life scenario that I think we have not touched a lot in this community. But I think there is, so my group actually spent a lot of time trying to build a case, and I need a lot of feedback in terms of how we build forward. So, but I'm not sure if that's the answer that everybody's looking for, but there is real life, real world application with the growing space industry.
So I listened to Nikki Fox's talk at the space weather meeting last week or something, and she was talking about the GDC mission, and somebody had asked a question in the Q&A afterward, and she said, you know, this is where the rubber meets the road. We've got satellite drag issues that we need to understand, and we need to be able to quantify and predict thermospheric density in order to get a handle and be able to forecast conditions for satellites orbiting the Earth, you know, in LEO. So that's one, you know, real life application, and we all rely on satellites to provide, you know, telecommunications and GPS and all that stuff, and we don't want them falling out of the sky. So we need to understand thermospheric density.
And yeah, there's no satellite falling out of the sky with the storm. If you're asking me that question, I've been asked every single day. But there is risk. There is issues that we did talk to a lot of satellite operators. So there are real world problems.
What about satellite debris, right? Did anybody see the news about how close old Russian satellite came to hitting Sabre and the timed instrument? Right, I mean, like that's an actual real life event that happened just 2 weeks ago, I think, that is very practical to our community. It's the longest satellite data record that we have that's still producing data. if that were to had actually been a collision, we really wouldn't have much monitoring the MLT region, right?
So we really need to do better job in neutral densification, and that's everybody's crying for it. But when you do that, you have to think about, can they use it? Are they able to use it in your way? And then, how do you, I didn't know that I had to help them out beyond building a model. And they asked me, how can I use your model in our satellites? How do we upload everything to our spacecraft? And I was shocked to hear that question. Like, I have no idea. My job is done. I give you the model, I give you a real-time thing. They're like, okay, now what to do with the interface with the spacecraft? So I think there are a lot of questions when we do a little bit step, but we just have to start from somewhere.
There are 3 more questions from the audience, so 3 minutes each question about.
I think Lin will just do one for now, and then if we can't answer, we have to stop.
Okay, all right. There is still time before dynamic GDC get launched. Meanwhile, how do we get new insights from comparative study of models and observations? Any suggestions?
I think, so I would argue that there's a lot of sort of untapped data out there. I'm not saying that we don't need to collect new data, because we obviously do, but I think that there's a lot of data that's just sitting on spinning disks that we could tap. I think that we have a tendency to want to look forward, or we have a recency bias, but there's a lot of data. Like DMSP is a fantastic resource that I feel like the community doesn't tap nearly as much as it possibly could. And there are just a lot of data out there that we could go back. And yeah, I'll leave it as that.
Yeah, in terms of recent stuff, in looking within our session, for example, NASA AW is a big data opportunity from a modeling perspective, and as well we have growing networks of instruments across the US and other locations, and for example, South America, that provide good science basis for investigations on the gravity wave side. Another source of data that has been huge is networked GNSS receivers. That has provided just a wealth of information about what happens dynamically in the ionosphere across a wide range of scales. So those are a big opportunity for us, I think.
And I mean, we also have missions in orbit that are, in my opinion, scientifically perhaps a little underused. I mean, if you look, for example, into the potential of cosmic or cosmic 2 electron density data, and I mean, these are constellation missions, and I mean, they deliver a spatial and temporal resolution that would be everyone's dream to have that in the neutral atmosphere, for example. And I mean, I personally see a lot of untapped scientific potential in missions like Cosmic 2, and we still have, of course, Gold operating and taking basically continuous images, photographs to a certain extent of the thermosphere and also the ionosphere.
And really quickly, I should point out that Tidy is still out there, so you can use neutral winds from 90 to 100 kilometers. It exists, and it's good.
Thanks for reminding us there. One more question.
So besides satellites, we should emphasize ground-based observations. There are unknown physics that haven't made to models, needing ground-based observations to discover. This question is from Xin Zhao.
Yeah, so ground-based instruments have been contributing to these CEDAR discoveries a lot. So this is undeniable. So as part of this AW mission, we do have a bunch of ground-based instruments, clusters, and also student collaboration opportunities with the other institutes focusing on ground-based observation instruments. So we do emphasize the importance of ground-based science investigations. And so yeah, well, of course, ground-based observation has its limitation. If it's possible, for me as a LiDAR people, I would like to establish a network of LiDAR instrument clusters surrounding a geophysical hotspot to conduct the temperature and wind measurements from the surface all the way to the thermosphere. So that would be ideal. But of course, a budget constraint is always a problem. So we just need to find innovative ways to persuade agencies to support all these big dreams. Hopefully, they can come true one day.
So the last two questions about comparing models to observations have been excellent. I would love to see every modeling paper include comparisons to observations. I know that's sometimes not possible, but it really adds to the validity of the paper when I see comparisons to observations. And satellite and ground-based observations can provide such a different view of the atmosphere, right? You can do a global comparison over months of time from, comparing with satellite observations, but the ground-based, you have a point location, and I did this a few years ago where I compared model output to SuperDARN, and so these are point locations, and talk about a rigorous test of the model. You're not averaging around latitude circles, you're not averaging over the polar cap like I can do when I compare to satellite observations, but it's just taking one point in latitude and longitude and comparing to the model output at that point. And the comparisons are a lot different. And I think it's really important to include these kind of comparisons in all of our scientific efforts when we are using models so that, the community can understand how close are you to reality. So it would be nice if the ground-based observations were easier to get, some kind of community repository for all of the LiDAR data in a common format that's easy to use. So I would maybe put that plug out there for all the ground-based modeler or ground-based observation collectors to help us use your data to compare to the models.
And I think Lynn emphasized a very important thing, right? So we as a modeling center, we don't know what to compare is the sufficient comparison. So how do we build that metrics within the community to do a sufficient model data comparison? Do I need to do 10 different data to show that model is right? Or do we pick the best we can do? That's what we usually do for an event. We pick the best case we have, right, to publish the paper. So I would encourage everybody to discuss more throughout the week. Do you have any comments?
I just wanted to add one thing on this. This is a neat question I see here, in part because I think a good question for modelers is how we can make our results more readily interpretable when they're compared with data. I think there's a lot of value to understanding the details of how an observation works, the perspective of an instrument, and its band passes or fields of view, et cetera. In terms of modeling, we can that way do a much better job in doing high fidelity comparisons and making apples to apples comparisons, but also in defining what other observations or strategies might be valuable in the future. So I like the idea of simulating for the purpose of defining future plans also. So just wanted to build upon those because those were two neat points.
Thanks. There's a question right there. Somebody want to deal with that? I thought we talked about it. I think everybody has their perspective on that. Sorry?
You just answered.
Yeah, I think so. I mean, you just say that.
I partly addressed this question because I saw this comment,
That's
and
right,
I thought it fit in perfectly with the discussion that we were having.
Yeah. And I actually have a couple of questions I wrote down and asked them in advance. And they start from if there's no funding constraint, right? So I do want everybody to think about if you don't have funding constraint, what will you do? What can you do? You know, because I also realize that I live in the box that, okay, you have this money, you do minimum thing you can do. But when we go out to the space industry, we start seeing that, what do you want? Do you want 100 spacecraft in a space so I can do a better space weather prediction? I say, yeah, that's what I want. I want spacecraft everywhere in the heliophysics from the sun all the way to the Earth. So think big, because I think there is a room to think big and not constrain ourselves in the way that, as a scientist, we are being told the way how we do it. So, if any final comments from anyone here want to share with everybody? No? Okay, and you want to say something, Mike? Yeah, go for it, if you want to say something.
Yeah, I thought I already mentioned my goal. You know, we build this network of a LiDAR instrument cluster. Each LiDAR is surrounded by imagers, ionosphere, FPI, and also this network is surrounding a geophysical hotspot. For example, the southern Andes hotspot, and also, of course, radars. So that was my thing.
So I guess I will say that one of the things that I find interesting as we get older, we tend to look at things that are more, quote, realistic to accomplish. And so we look at like cost constraints and stuff like that, and we think inside the box. And younger people in the field don't really understand the boxes at all. And so they think way outside of the box. And so it's absolutely fantastic to have younger people contributing to these types of discussions, because they may come up with like really innovative, cool ideas that may be more acceptable to the community than somebody who's like, well, you know, our cost constraint is blah, 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 so we can do one LiDAR in the middle of, you know, Colorado, and that's it. That's all we can afford, so let's all just propose that one thing.
Right.
While a graduate student may say, like, why don't we distribute them everywhere and do new techniques and stuff? Yeah.
Exactly. I mean, I see that when NOAA set up the requirements, they will base on the current instrument technology, right? I say, but I want this ON too. I don't care how they do it.
Yep.
I want it, right? So think about beyond the box. I think that's what that we want to share with you.
Yep.
Thanks all our panelists again, and I hope you enjoy it. Thank you.
All right, so we're breaking for lunch now, and we'll be back at 1:30 with sessions. I have a couple of announcements, though, before we do. There's a mentor-mentee lunch in the porthole room, so please attend that. And then, Mark, there's a CSSC dinner tonight at... Okay, we're going to meet, if you're in the CSSC, meet in the lobby at 6:30 tonight for the CSSC dinner. All right, everybody, have a good lunch.
Thank you so much.